In the next session of nanotechnology, we have one oral talk by Ivana Katarina Munda, who is a PhD student at the University of Zagreb, Faculty of Chemical Engineering and Technology, Zagreb, Croatia. And the title of the talk by Munda is Characterization of Sol Gel Derived Ceria Nanoparticles Doped with Manganese. So I invite Miss or Mrs. I don't know, Miss Munda. So please.
Miss. Thank you.
Okay, thank you. Thank you.
Thank you for the introduction. I hope everyone can hear me okay.
Yes.
I'm Ivana Katarina from the University of Zagreb, and I will share with you my presentation.
Yes.
Okay, so my presentation and my topic today is the characterization of ceria nanoparticles derived by the Sol Gel method, pure and doped with manganese in various amounts. So let's start with a little bit of theory about ceria. Cerium oxide, cerium 4 oxide, also commonly known as ceria, is one of the most important compounds of cerium, and probably the most used compound of lanthanides in general. It's relatively cheap and easy to gain, and so it has a widespread use. It has a very stable fluoride structure with a space group of Fm3m. It is stable for up to 240 degrees, which is also its melting point. It has two interchangeable oxidation states, cerium 3+ and cerium 4+. And that also provides it high oxygen mobility and some other properties which makes it very easy to use. Cerium 4 oxide is known for its oxygen vacancies. It's used mostly in three-way catalytic converters because of its vacancies, which are easy to make, and it oxidizes carbon monoxide, hydrocarbons, and also can be used in the reduction of various nitrous oxides. It's used in solid oxide fuel cells due to its ability to store oxygen in its structure, and also as in supercapacitors. This on the right side is an example of how the oxidation of carbon monoxide works on ceria as a catalyst. Carbon monoxide uses oxygen from the ceria structure, and the vacancy is then filled with an oxygen atom from the air around it. Now that we know a thing or two about ceria, let's begin with synthesis. For our synthesis, Sol Gel was used because of its low price, quality of product, and of the possibility to better control the parameters during the synthesis. For our synthesis, we used acetyl acetonates because they are rarely used and problematic. In most of the papers on ceria, authors gained the nanoparticles with the use of nitrates, But the problem with nitrates is that they have then you have an impure product, and it's hard to get rid of nitrates after the synthesis. We used acetyl acetonates, but we stumbled onto a problem. There, the solubility is very small in many solvents. It seems that the metal ion significantly influences on the solubility of the complex in general. There's no data for solubility in water. And we tried quite a few times to solve this problem before deciding that the double solvent is the best solution for this. This slide is called the Solid Gel Adventures because it was. The top left picture shows the evaporation of solvents in 7 days at room temperature. The left bottom picture shows the dissolution of 2 grams or 4 grams of precursors in the solvents, and it can be seen that the color varies depending on the mass used. For example, for the bigger mass, the 4 grams, the color is black, which indicates that there is more organic phase in the sample. The right pictures show that we gained gel-like structure. It's semi-transparent and it doesn't flow. For the results, we have the characterization of the samples. We used X-ray diffraction, differential thermal analysis, Fourier-transformed infrared spectroscopy, and Browner-Emmett-Taylor for the specific surface area. So the X-ray diffractograms show the amorphous gel structure. They have a characteristic bump at about 28 degrees to theta, which indicates the amorph phase. They also have some faint peaks here it's 10 degrees to theta, 12 and 23 approximately. It was a problem to determine which of the precursor or other phase is this, because in the ICDD database there are no known data for cerium acetyl acetonate with 3 acetyl acetonate groups, only with 4. And the manganese acetyl acetonate in the database is not an exact match, probably because during the synthesis it loses some of its acetyl acetonate groups and has then a slightly different structure and shows slightly different maximums. Differential thermal analysis was used to gain insight into the thermal decomposition of samples, mainly organic phase in the sample. As can be seen, the thermal evolution of gel samples can be roughly divided into 4 steps. First step is from room temperature to about 170 degrees Celsius. It represents approximately 3% of the mass lost. and represents water loss mostly. The second step is from 170 to 350 degrees Celsius. The mass loss is bigger here, it's about 10%, and it's mostly attributed to the crystallization of cerium, ceria. The third step from 350 to 490 then represents a 14% mass loss, and the final step is from that temperature to 1000 degrees, which represents 16% mass loss and is probably due to organic phase and carbon carbon loss. Fourier-transformed infrared spectroscopy. We here are all spectra for the samples as well as the precursors. We can see the characteristic vibrations of the carbon oxygen bonds, as well as the metal group bonds. And here are the structures of the precursors. When we combined the FTIR results with the XRD analysis, we actually combined them to determine the best annealing temperature and the thermal treatment temperature. There are almost no leftover organic phase while quenching at 300 degrees, which is shown on the FTIR. But on the XRD, we see that quenching at 300 degrees shows some leftover amorphous phase. While quenching at 600 degrees gives us no leftover amorphous phase, and from the FTIR it's visible that there is no leftover organic phase, but the maximums are very narrow and high in intensity, and that means they have a big crystallite size. Crystallite size is also shown in the table. So quenching at 300 degrees gives us 4 nanometers approximately crystallite size, and quenching at 600 degrees gives us 18 nanometers. For the thermally treated samples, we treated them at 500 degrees for 2 hours. These are mostly for future comparisons, because we here in the department are trying a few different synthesis approaches for gaining ceria, and so we must have all of the samples at one temperature for 2 hours, let's say, so we can compare them and see which synthesis method is the best. Crystallite size was calculated by the Scherer method, and here is also the equation. In the table we have the crystallite size and specific surface area gained by the Brauner-Emmett-Taylor method. We see that the undoped sample has much smaller specific surface area and almost 3 times bigger crystallite size. And the doped samples are definitely better for, let's say, if it will be used in the catalysis. On the right side, we have an XRD diffractogram, which is mostly here, so you can see the difference in peak intensity and the broadening, from which we can also deduct the size of the crystallites. These are various samples treated at 400 degrees for 2 hours. Grain growth, here are the results for the grain growth kinetics. The samples were thermally treated for 2 hours at different temperatures to gain a non-isothermal kinetic system structure. Here, these are the plots for all of the samples treated at 250, 300, 350, 400, and 500 degrees. The activation energy and pre-exponential constant were obtained from the plot shown here. And according to the equation in the presentation, the one on the top, in the top, let's say, right corner, that's used for the calculation of the pre-exponential constant. Here are some other results from the kinetics. As can be, just a second, I just wanted to say here that it can be observed that for the non-doped sample, as well as the 10% of manganese doped sample, the fit is fit of the straight line, linear fit, is very good, but for the 20% and 30% doped with manganese, it's not so good. The coefficient of determination and the this is actually the pre-exponential constant and the activation energy. I gave you here tables from the linear fitting, or in these are from the previous slides, but this is a table. It can be observed that the undoped sample has higher activation energy than the doped samples, and it would mean that it has smaller crystallite size with thermal treatment, but that's not true. After looking at the pre-exponential constant, it can be seen that all the doped samples have smaller pre-exponential constant, and that is why even if the activation energy is smaller for the doped samples, the growth of the crystallite is slower than the growth of the non-doped sample. It can also be seen that the sample doped with 20% of manganese is not in order with the other samples, and its R-squared value is pretty low. That means the linear fit is not good for the data given. So we will probably do the testings again. So in conclusion, I can say that ceria can be synthesized by the Sol-Gel method. Acetonates can be used, but are difficult to dissolve. Faint peaks of manganese acetonate are visible for all of the doped samples after the synthesis, thermal treatment is mandatory to gain nanoparticles. All tried thermal treatments result in nanoceria, even at 250 for 2 hours. Crystallized size is smaller for the doped samples, and specific surface area is in concurrence with that. Activation energy is smaller for the doped samples, with the exception of the 20% doped manganese, but we will be doing the test again, so to see if the problem is with the temperatures or with the sample, maybe try the synthesis again. So thank you for the attention, and if there are any questions, feel free to ask.
Thank you, Ms. Katarina. Now the participants can ask questions, please.
Yes, Professor.
Yes, please ask.
Thank you, Ivana Katarina Munda. Thank you for, I hope that I pronounce it well.
I didn't hear you. What did you say? Sorry.
For now?
Please repeat your question. She is
Okay.
able to understand. Yes.
Thank you, Ivana Katarina. Thank you for your presentation. I have a question concerning the. Is there an additional application actually for this nanoparticle or not?
Yes, there is usage of ceria nanoparticles. It can be used as a catalyst or in self-cleaning ovens even, or as a polishing material for something that has a hardness similar to it, so about 6 on the most scale.
In biological field, no?
I'm not sure. Sorry.
Thank you very much.
Any other question? Ms. Katrina, I have 2 questions. The first one is, why did you choose to dope manganese in cerium oxide? And the second question is, you calculated the activation energy. The activation energy does not show systematic behavior, means it is not linearly increasing or decreasing with manganese doping.
We used the manganese for the doping because we tried doping with various transition metals, and we tried to gain catalytic activity for toluene, and the manganese doped sample in 10% had the best catalytic activity, and the lowest temperature for conversion of 95% of the toluene. So we tried to dope with more percentage and see if we will see if it will be better, or we hope it will be better, even better for the catalytic activity.
And the second question is about the activation energy. Why it is changing randomly with manganese doping, with increasing manganese content?
Well, the activation energy, we had a problem with the activation energy. When it's smaller, the activation energy for the, let's say, doped sample is smaller than the non-doped sample. And that usually means that the non-doped sample is better, more thermally stable. But then we tried when we saw the crystallite size gained by the Cerium method, we saw that that is not the case. So we tried to gain insight into what is the determining factor for the growth of the crystallites, and we compared the results for all of the samples, and saw that the pre-exponential constant is, let's say, in concordance. It has a trend, so we tried to explain it by that.
Okay. Any other question from the participant? I think there is no question, so I would like to thank Ms. Ivana Katarina for a wonderful talk.
Thank you.
And with this, we come to an end of the 2 sessions, and now it is time for lunch break. So enjoy your lunch and join us in the afternoon sessions. Thank you very much. Thank you, everybody. Thank you, all speakers.
Thank you.
Thank you. Bye.